Gariel, who is the CTO of Xwing. I'll give a short intro to Maxime. He's a graduate of Super Héros, class of 2003. For those of you who don't know the French system, Super Héros is the lead aerospace industry university, co-located with Airbus Industries and many of the other members of the ecosystem of the aerospace of France. Following that, he went to Georgia Tech, where he received his master's and PhD also in aeronautics, working with Eric Ferron, who is my academic cousin. Guess that makes us second cousin-ish or something like this in the academic geological tree. He then went for a postdoc at MIT, also worked at NASA on air traffic management, I believe in the AFC branch, Rockwell Collins for a few years until he finally became the CTO of Xwing, where he has been for now the last 5 years. So with this, we're very excited to have you here, Maxime. Welcome.
Thank you. Thanks for having me. Good afternoon, everybody. Very excited to give this talk about what we do at Xwing, but also why we're doing it. I think it's very important to think about the technology, but why is this technology happening, and how it's going to impact the future, how it's going to impact people, and especially regional air mobility. So by regional air mobility, we think about distances that are typically too long to drive, but too short to fly commercial airplanes, so like 50 to 500 miles. Distances that when you need to go someplace, there is no alternate to your car. There is no bus, or very few buses, there's no train, there's no commercial flight. So how do we solve that gap in the transportation landscape? So you already did that, so I'm going to skip my introduction. And we're going to show a short video about the technology. So sorry, that's...
Xwing Caravan Conquer ground, runway 1, left, taxi via Gulf.
3, 2, 1.
Xwing Caravan clear for takeoff.
Autonomous flight technology pioneer Xwing is looking to take a leap forward.
A technology that could transform the business of flight in every part of the country.
Making aviation history with its demonstration of the first autonomous gate-to-gate flight with a commercial cargo aircraft.
The company hopes to begin commercial freight operations in 2022.
Just got back from a fully autonomous flight with Xwing. It felt like a normal flight. It wasn't scary at all.
On our approach in the Xwing plane, the computer kept us on a perfect glide path to the runway.
It's a one-click solution. You select an airport, pick the appropriate runway, build a flight plan and a trajectory to get there, and execute that.
It could be the beginning of a new industry that makes affordable deliveries to small, overlooked airports all over the country. Suddenly, thousands of small U.S. airports could be shipping hubs.
Xwing has control.
So that's a video from 2021, and we have actually started commercial operations. So that's the good news. So to give you a few facts about air transportation in the US. If you think about your closest airport, which one is it? What is it? Oakland. And then after that, how long does it take to get to San Francisco right now? Maybe. If you leave right now, I think you're going to be there at 5 or 6 p.m. But anyway, it's actually like we are very lucky, lots of airports where we are. If you think about the country, everybody's within 16 minutes in average to their closest airport. So even people drive hours to go to Chicago or to go to a large airport. We have 5,000 small airports in the US that are not being used, right? And so 60 minutes is very important. Only 1.6% of the trips between 50 and 500 miles are being taken by air. So people are driving for all of those distances. And a 500-mile trip takes many, many hours. Right? There are $3.2 billion being granted by the federal government to small airports. So this is a resource that we can use, that the government is funding, but that very few people benefit from. And 0.6% of all of the airports in the US support 70% of domestic air travel, right? So think about this, 0.6% of the airport supports 70% of domestic air travel. And this is shrinking by the day. And I forgot why we have this 95% energy reduction from what it is, so I will skip that stat. But if you think about where we are right now in terms of technology, there are two key technologies that are going to change air transportation. The first one is autonomy. One of the major challenges is to have a pilot in that aircraft. With autonomy, we can move this person from the airplane to the ground and still supervise and provide this necessity to have somebody talking to you or to air traffic control. But you can really change those small vehicles. And then eventually we're going to have electrification, making those airplanes clean, making them like less noisy to reduce the cost. So with the advent of autonomy and electrification, we're going to have a new mode of transportation that will be small autonomous airplanes. Some can be used for urban air mobility, so like within the city from here to Mountain View, for instance. I hear that's interests somebody. Or you can go from small airport to small airport. As I said, most of the regional trips are used by car, and that's the only viable option. And I think that's exactly what we talked about earlier. If you think about long distance trip, commercial air travel is fast, affordable, and efficient. You cannot beat an airliner in terms of cost per seat passenger mile, right? This is by far the cheapest, but that will not take you everywhere. It will take you from a large airport to a large airport. Then for regional distances, as we show here, you don't have a choice. It's only your car. We have, in 2001, there was like 3.5 billion trips, which cover 1.3 trillion miles, and 93% of those were done by cars. It's an enormous market, and yet we don't have a good solution. But for urban, in the cities, we see that we have a ton of options, and we should have more. Like you can have your bicycle, you can have your electric scooter, your car, your taxi, Uber, personal, trains, metros, lots of good solutions. But for this 50 to 500 miles market, there is no option besides your car. As we talked about, this is how the 3.5 billion trips are distributed. 50 to 500 are done using your car. A few of them are using, very few are using air travel and other means, so maybe some people take the bus. And as you get further along, like 250 to 500 miles, you start having more of those trips being done by air. So you can see that the airplane is being used, but not a lot. And the objective of our technology is really to capture some of those trips and to reduce the time that people spend driving. Kind of amazing that by just putting the map of all the airports in the US, you can really clearly see the US and the country. So we really want to use this infrastructure that was built in the 50s and that is funded by the taxpayers and not being used. So 95% of the US population lives within 15 miles of one of these airports. I guess you probably have read the news in terms of loss of pilots. So actually, before COVID, there was already a pilot shortage, and COVID amplified that because many pilots were offered large sum of money to retire prematurely because all the airplanes were grounded, and now they don't want to come back. So the airlines are hiring all the pilots for their long distance trips because that's what pays the most, and then the result is that all the pilots for the regional airlines go to the large airlines, so all the small routes are being cut off. So communities, small towns that used to have one flight a day, 2 flights a day, now have one flight a week, and sometimes nothing at all. So it's really causing a lot of, I don't know how to say it. It's isolating those communities even more than before. Those people have to drive now several hours to get to the large airport if they want to commute. It's causing some hospitals in some places to close because the doctors cannot go there. You have many small towns where they bring doctors from a large city to the small town for 2 days a week, and now those things cannot happen anymore. So it's really having a negative impact on a lot of small communities. How can autonomous flight impact our daily life? So first of all, it's going to have more reliable deliveries for more people. You don't rely on having a pilot with the airplane to be able to do your routes. You can have a pilot located anywhere in the world controlling an airplane that is someplace else around the world. So you can really use your airplane and start doing deliveries and chaining all those cities. You're not constrained with having a human with the aircraft. It's going to revitalize small towns and communities. We get emails on a weekly basis from people in Canada, from people in Alaska, where those airplanes are their lifelines. The only way they get fresh food, they get legal paperwork, medication, is via airplanes. Otherwise, the drive might be like 8 hours, 10 hours, and some places don't even have roads between the communities to the large city. So it's really like a lifeline for all those people. It also increases safety. Lots of the pilots, a lot of the accidents occur because of pilot's error, or when they go into weather that they're not supposed to be and lose control of the aircraft. So by having the same level of safety that airliners have on small airplanes, we can really make those systems safer. And eventually, also by optimizing your trajectory, you can reduce emissions. So we estimate we can save 8 to 10% without electrification on emissions. So our goal at Xwing is to build the world's smartest, cleanest, and most accessible air transportation network. So really, by optimizing from end to end the entire so technology as well as operations. How do we get there? First step is solve the engineering problem. So automate the aircraft, move the operator from being a pilot to being somebody who clicks and supervises a number of airplanes. Then we also need to fly cargo, right? You need to learn the craft before you can pretend to improve it. So we do those two things, and eventually, once this technology is ready, we want to move to passengers. But first, we have to prove that we have technology, that we have a safe system, and we can really get better. Where we are, so the company was founded in 2016. In 2018, so 2016 to 2018, we looked at what does it mean to replace a pilot? What does a pilot do, and what are the challenges that we have to do? Flying has been automated for decades, so this is not something difficult. What is difficult is really to replace the eyeballs and the brain of a pilot. Replacing the hands, we know how to do that, but replacing the brain and the eyeballs, it's much more difficult. So solving for when you taxi the aircraft, seeing other vehicles and avoiding them. When you fly, seeing other airplanes and avoiding them. Talking to air traffic control, making the decisions that will lead to a safe flight. So we identified this problem early on, and then we worked in 2018 with NASA and Bell on this product called Detect and Avoid. So it's the ability of the airplane to see and detect other aircraft and avoid them. So things that the same problem that autonomous cars are doing. As a human, we're really good at it, or we're somewhat good at it. But as we don't have the technology, or we didn't have the technology 5 years ago for airplanes to see and avoid each other. So this is something we've worked with NASA for a number of years. Back in 2019, then we acquired our first aircraft. So it's the one that you saw in the video. We got in July 2019, we started opening it up, installing our flight control system to do our first flight in December 2019. Then March 2020, something happened. We all went home. But we came back a month and a half later to be able to do our first takeoff to landing mission 8 months after having the aircraft. So the team has really, went really fast to be able to do all of that. And then after that, we worked on auto taxi so that we could, in February 2021, do a gate-to-gate flight, which I'm going to show a bit later. But so gate-to-gate from standing on the parking to taxi, taking off, flying through the airspace, landing, and taxiing back. So solving the entire challenge. We did that in 2021. And now, at this stage, we are operating flights from controlled airport to uncontrolled airport. So let me give you a bit of a background here. So when you fly at a large airport, you have air traffic control that dictates who does what. So they're going to tell you Delta 123, you can taxi to runway 19 right using taxiway Alpha, Charlie, and Delta. And the pilot can only do what air traffic control tells them. So that's for the large airport. When you get to a small airport, like where we want to go in the small communities, you have a runway, a piece of concrete or asphalt, and there are rules in the book, but people do whatever they want with that airspace. So when you get there, you have to see other airplanes, you have to use your radio to talk to those people, to sequence yourself, and to avoid and make sure you don't run into one another. So kind of same as driving, but you're flying at 150 miles per hour, and the other people is really far away, and you have to see them. So it's quite challenging. So we're able to do that now with an operator located in one location, flying the airplane pretty far away, and we have all the sensors and all the technology to be able to do that safely. So what do we need to do? We need to have an airplane that is able to communicate with our network operating center. So have a location where we have a number of operators that can control a large number of aircraft. We need to have sensors on board the aircraft to detect all of the other airplanes. We need to have redundancy on all the systems. So like if you have any failure, you need to keep on flying, right? When you go onto an airliner, you don't think it's going to be safe. Safety is a given in aviation, but it's extremely hard to achieve. So we need to have that at a price point that makes sense. So things that you have on the large Boeings, now we need to bring that down to smaller airplanes. We have algorithm to optimize our path planning so that you can save fuel, you can save time. We need to do taxi, takeoff, navigation with a really precise positioning as well as redundancy. We need to handle all types of failures. So if you have an engine failure, we need to be able to detect it and mitigate those type of failures. And then we need to have a platform agnostic system architecture. As we think about the future, this is our first platform. We want to get to a world where we transport people all across the US and the world using the small airplanes. So we need a system that can be transposed to other airplanes in the future. So this shows like roughly what we add to the aircraft. So taking a step back, you've seen over the past few years a lot of electric vertical takeoff and landing vehicle being developed. Uber Elevate kind of launched that. So small airplanes, new airplanes that use electric propulsion, batteries to fly you across the cities. I think this will come in 15, 20 years. But before that, the only way this will scale and will be, you have a lot of them flying across the airspace is if you don't have a pilot on board. To have a high density of those vehicles, they have to be automated. First, it's going to be really difficult to find those pilots, to train them, and they will not be able to make decisions fast enough to avoid accidents if you have a density of those flying vehicles. In 2D, we're pretty decent at it. We still kill 36,000 people a year on the road, and we killed 0 when we fly. So we need to get to that level of safety. So what we're adding are those blue pods under the wings that contains all the sensors that you typically see on self-driving cars. So LiDARs to detect, as we taxi, to detect other airplanes, to detect wildlife, detect the fuel truck or people. Where we fly, we use radars to detect other airplanes. We use also like a system called ADS-B. So it's using the transponder on aircraft, we broadcast our position and we can receive the position of other airplanes. So it's a great way for some of the airplanes to communicate with one another, but not everybody has it. And then we add all the black items, which are redundant actuation, redundant compute, redundant positioning systems. And here, I'm sorry, it's pretty small. That's our control center from which we operate this vehicle.
What is the range of the radar?
So the radars, we're looking at 3 miles. Yes, so that's a very interesting question. Like people are just like, why don't you use the same sensors as on a car? In a car, you care about like 200 meters, 300 meters, right? Because that's the distance you need to stop. When we fly at 170 knots, which is 190, something like that, miles per hour. The other person does the same. That's 400 miles per hour of closing speed. So to detect reliably, to be able to take action, like as an airplane, we don't do it's not Top Gun, so we don't do like crazy maneuvers. You need to have like a smooth maneuver. So we need that range. So that makes for a pretty big radar and a powerful system. Any other question? Don't. Sure.
With the planes, will you be operating in uncontrolled airspaces then?
No, both. We need to be able to, I think I'm going to get to it. Yes, we need to operate from controlled and uncontrolled airspace. I will explain why in a minute. So when we think about it, the flight is the phase that we see the most, right? But we have to really think about before the flight to after the flight. The pre-flight, like how do you load the airplane? When you load an airplane, the CG is extremely important. If your CG is too far forward or too far back, you're not going to be able to control the plane and you're going to crash. So think about right now you have a pilot of the airline that knows how many people they have. They do statistics about an average how heavy you are. But on small airplanes, you really look at what is the weight of each passenger, where they're located, how much fuel you have to make sure your CG is going to remain within the range you need across the flight. So how do you do that autonomously? It's a really good question. Then through the takeoff, making sure you are along the runways, things that humans are really good at doing, like looking at the runway, making sure you're straight, it's much harder for sensors to do that reliably. As we fly, running other airplanes, in approach, we can be guided by air traffic control. So ahead of time, you don't know exactly what trajectory you're going to have for the entirety of the flight. So we need to be able to react to air traffic control, changes in trajectory. And when they talk to us, we need to be reacting really quickly. Air traffic control does not like you to take a few seconds to react. So we need a way to reliably communicate with the aircraft to be able to send what ATC tells us to do. Then land and taxi back. So I'm going to show you a video that shows from February 2021 that shows the gate-to-gate process. I'm going to put the sound at the beginning, and then I will narrate as we go.
Xwing Control, test radio check. Test Xwing Control, have you out and clear. Test Xwing Control, ready for engagement. Engagement.
Oh.
In 3, 2, 1. Xwing has control. Xwing has control. Xwing has control. Xwing control is ready for ground block.
So the first thing we do is the pre-flight check. As we engage the system, the aircraft checks all the control surfaces, all the servos, all the computers, checks the engine to make sure everything is safe before we go for flight.
Ready to taxi. Roger.
Oh.
Xwing Control, ready to taxi. Conquer ground, Xwing Caravan, PSA, ready to taxi, 1 left for takeoff with information mic. Xwing Caravan, Conquer ground, runway 1 left, taxi via Gulf. 1 left, main ramp to Gulf, Xwing Caravan.
So ATC gave us the taxiway, so the operator just types in which runway to go to, the taxiway, and the aircraft generates a path. And as we go, we use the LiDARs to detect all the objects and stop the airplane if we see anything. Then based on where we are, we're going to have different speed limits so that we don't cause any issue. Right now, we're using mostly GPS for positioning. We're looking at using vision to follow the line and to improve the integrity of GPS. A lot of the work also has gone into optimizing airport operations. The airport needs to operate very efficiently, so you need to, you cannot wait to be ready. So the airplane is able to, we communicate with ATC very early on so that if they clear us for takeoff, we just go on the runway and roll so that we don't wait. A lot of the drones that you see, they're going to get on the runway, wait 5 minutes to be ready, and then take off. We need to be able to be expeditious. That's really important in this large-scale transportation network where every second counts. So in this case, we optimize for runway length. So we go automatically to the end of the runway. We take off. As we accelerate, the airplane checks that the airspeed is working, that all the sensors are fine, determines if it can proceed for takeoff. At 80 knots, we rotate. So that's the phase when you go from airborne to flight. Then in this case, we're just doing like a lap around the airport to demonstrate the end-to-end goal. Like the flying portion is not as relevant. So as we go, I'm going to pause here for a second.
Is that a video feed streamed directly from the aircraft?
So currently we are able to downlink that, yes, to feed that to the ground. Eventually we don't want to do that because that's a lot of data to downlink. So we are summarizing this data in only the key important pieces that are actually, hold on, that are here. So here you have really the useful data. So here what we see is we've used 4 cameras that are under the wings of the airplane. We add terrain database. This is mostly for remote operator to know what's happening and making sure that we're not going to run into terrain. We display our path. We display all the other airplanes that we detect. So those are like other airplanes, and you can also see it at the top here, detected like 13,000 feet away. So it's in feet and not in meters. Yeah, in aerospace we use like random units. And that helps the remote operator to sequence itself into the traffic pattern at uncontrolled airport. When you get to a controlled airport, ATC is going to tell you like where to go, so that make sure you come like a minute and a half after the previous airplane. When you get to a smaller uncontrolled airport, you have to find all those people to be able to sequence yourself. So that's the remote operator. That's, yeah, actually. So this is the main screen. Can you see me? Yeah. That's the main screen where we synthesize all the information. That's where like all the decision is being made. We stream right now the screen you just saw, and that's really to help as we synthesize this data in the center screen. We have this video feed also of the pilots. We just show the pilot is not doing anything. So since we don't have the redundancy in place yet, we have a safety pilot that allows us to fly out of Concord. So we are based just behind the mountains, and that's where we fly out from. If we didn't have a pilot, we'd have to go like hundreds of miles away in the desert to do this test. So the nice thing is that we can do that right here. And then we have a video feed at the airport. We have a camera that tracks the airplane, so we can also see what's happening. Even though those operations are quite complex, we have a single person handling the flight, and that's really important. Like we're not NASA, we're not like SpaceX. We don't want like 50 people watching the airplane. As we come in for landing, the airplane checks itself, check that the brakes are working, that we have the right sensors to measure altitude, that the GPS is good before proceeding. Then the airplane gets onto the runways, does a smooth flare. Rolls to the slowly actually like uses reverse thrust to minimize wear and tear on the brakes. So as we think about these operations, it's not only the cost of the flight, but it's like maintenance is one of the highest costs in aviation. So being able to optimize to reduce maintenance cost is very useful. So here, based on the runway length, we're going to maximize. We're just going to let the airplane decelerate as much as possible, use reverse thrust before we use brakes, for instance. And then we taxi back. So, oh, interesting. The top of the video is cut off. And then we taxi back home. So I'll move on. As I was describing this morning, not this morning, just earlier at the beginning, first we automate the aircraft and then we fly cargo. So getting just the technology is first part of the strategy, but if you want to deploy this technology and you want to deploy commercial transportation, you not only need the aircraft, you also need to have your operator certificate. You need to be an airline. If I had enough money, I could buy a Boeing 737, but I would not be allowed to fly it, right? Because I don't have the right qualification to do it. And then I could get my pilot license to fly this airplane, but I would not be allowed to fly with passengers behind. So at some point, like the FAA, it's not just about the aircraft, it's also about showing that you can maintain that aircraft, that you can do all your planning, that you can train the pilots, you can train your mechanics. So we're doing those two things at the same time. Since we're going to have a new type of airlines, an airline that doesn't fly traditional airplanes with traditional pilots, how do we train our remote operator, right? How do you maintain this aircraft? What are the operating limitations of this airline and this operation? So we have started our own airline. Right now we are flying with a traditional aircraft. So the same aircraft we have, they're not autonomous yet, but we're using those to collect data to understand what it means to fly day in, day out. What are the challenges we're running into? What does it mean to be ready at 5 a.m. on the ramp? What kind of crazy or unexpected commands air traffic control are going to give us? So by flying all those flights, we collect the data, we analyze it, and we can get to a better product. So right now we have 35 airplanes flying for UPS every morning, every night. Those are feeder routes. So it's really when you send a FedEx or UPS package and it's overnight delivery, it means it's going to get onto an airliner that will get at 5 a.m. at a location. Then it's going to go into a smaller aircraft to do the last 100, 150 miles, and then go on a truck to your house. Right? So we're doing this portion between the large airliner to the truck. So again, this is when I go back to the most important message here is this is the first step towards using all of the airports we have in the US and then eventually around the world. We are taking this slow approach by doing the technology, doing the airline, flying cargo first because cargo does not complain and cargo is not scared of not having a pilot in the front. And once we have that in place, we will move on to passengers. Again, we can have the debate about not urban. So we had lunch and we're discussing like urban air mobility versus regional air mobility. The way we see it is urban is between the cities, places where you could use the metro, less than 50 miles, and you need a VTOL, so vertical takeoff and landing, because you don't have infrastructure. In this case, for where we are, we really want to use all the small airports. We want to use those runways because that's also where the electric vehicle will be able to have a decent range. If you need to use electricity for vertical lift, you're using so much on the takeoff and landing that then you have no range. With the current battery technology, we estimate that you can have a 200 to 250 mile range conventional takeoff and landing airplane that can serve this market. And this is my last slide.
What is the contingency management plan when you're flying, say, over an area? Say there's mechanical failure or something else happens.
So for all the failures, like engine failure, for instance, there are two ways to think about it. First, you can think about it as how do you plan your route, right? And then what you do once you have your failure. So we have algorithms that at every point in flight looks for alternate airports, knows your glide ratio, knows the winds, and will take you there. And then you can also run that offline before so that you plan your route so that if you have this failure, you can always glide to such an airport. So it's planning for contingencies ahead of time and also have algorithm in real time to manage that. We have all the redundancy in place so that any failure has a way to be detected and mitigated. So no single point failure, there's no single point failure on that airplane.
I know you mentioned before that you may want to do other things nearby to avoid any collisions while on the runway. I was curious if the plane has any sensors on board that can communicate with weather services in lifetime, like if any thunderstorms come up or anything unexpected.
Yes, so that's a very good question. So weather is one of the things that are extremely important in aviation. So one of the beautiful things is like on the ground, we have access to really good data. So what we do is we get all the weather information from various sources on the ground. So the operator can then upload a trajectory. But also on board, we have weather radar and can use that weather radar information for live data as we fly. So like having weather radar is a requirement for the type of operation we have. So we feed that into our system.
Are you actively sensing wind or other terms of disturbance when you are flying, or you just treat them as additional disturbance and noise and use the ground information to deal with that?
Yes, so the wind is being actively sensed. The time when it really matters is before landing. And what is good is like when you land, you can sense between your airspeed and your ground speed, you do the math and you can get accurate wind. And then as we come for landing, we use that information to put your ailerons into the wind so that you don't flip the aircraft once you land. On the river side, when it's taxiing before taking off, we don't have a way to get the wind. Like the aircraft doesn't have enough sensors to get the wind when you're on the ground. So what we do is the operator inputs the wind from the weather station at the airport. So all the airports have a small weather station. So we use that we manually give the aircraft.
First of all, it's a great innovation, and from the idea to the product. I have a couple of questions. First, correct me if I'm wrong. As you said, so the aircraft is operating by a pilot, right, on the ground?
So it's operated by. So it's an operator. So it's not somebody who has it's not remote piloting. We don't have a joystick. We don't have pedals. It's really like point and click interface where the person manages the trajectory. It's really a trajectory manager rather than a pilot.
Okay, so far, is it like just your first stage, or it's going to be always like the same? Because my question is going to be 100% autonomous in the future, or you still need someone like to monitor the process?
So the goal is to get to the full autonomy, right? But we're integrating to an airspace where you have other users, and right now it's managed by air traffic controllers that talk on the radio. And if we want to have this technology happen, we cannot change that, right? We cannot change for air traffic management to change. Actually, it's funny. Like I did my PhD in 2006 to 2010 on air traffic management, and then I had job offers for there. I was like, this is way too slow. I'm going to go work on the aircraft side because by the time I do some innovation on the air traffic management side, I'm going to be retired. So we cannot count on air traffic management to change. It's a very, very slow-moving system. So we need to integrate our aircraft in that environment and deal with it. So that's why we have this remote operator that can talk to air traffic control and can supervise the system. As we increase data communication with the airplanes, so it's happening right now. Large airplanes in some parts of the country can get digital communication with ATC. As we have more and more of this, then there will be less reliance on the human on the ground to talk to ATC. So initially, it's going to be one operator for one airplane. And as we show that it's safe, that we show that we have enough bandwidth for that operator, we're going to have a second airplane, or maybe like two operators for three airplanes, right? Because then it's really about being able to handle the communication with ATC.
Perfect. And just very quick, other one. What would be the largest passenger aircraft that you are aiming to apply for on your next stage?
I don't have an answer at this stage, so we are really focused on getting this technology to market on the cargo airplane. Then the question is, where does the technology go after that, right? There are applications for large airplanes, Boeing, Airbus, they all want to go to single pilots, right? Pilots are a pain to have. There are not enough of them. And when you have cross-country flights, sometimes you need 4 pilots, right? Because the flight is just too long for the pilot to be on duty the entire time, and you need 2 full crews. So can you go to 3 pilots, like for this long flight? Can you go to 2 pilots? So there's a lot of applications for large airplanes. For all the small airports in the US, it will have to be small airplanes. Otherwise, the economic will not work enough. Like if you have a bus, you need to have enough people to fill the bus before it's economic to do it, right? If you have a bus that flies with nobody on board, you lose money. So it's going to have to be small airplanes at first for all those airports. And as the demand increases, you can have larger and larger airplanes.
The question was because you mentioned this area, like let's say Bay Area, that including like the total trip that has been done by people in a car. So you're trying to get a one segment of those users to bring to your, let's say that project. And
so
what is your target market of those in that segment?
So here we have 50 to 150 miles, and then 150 to 250 and 250 to 500. We believe that here we can capture like 4 to 7% at most of this, while here it's like 35% roughly, right? Because here you have little time savings. Right? For people to change mode of transport, you need to be faster and you need to be cheaper, right? Not necessarily cheaper, but like not that far more expensive. So few people will be able to pay a lot because they value that time a ton. But also you have a pain, right? If you have to change mode of transport, that's like, would you change, like get off your car to go into an airplane to save 10 minutes? Probably not, right? To save 2 hours, you would probably do it, right? So that's exactly where we think we're gonna make a small dent here, a larger dent here, but at the same time, the number is so big that it's going to be, it's a huge market.
Thank you very much.
Welcome. Other questions?
So, yeah, thank you for the presentation. My question is more from the airport perspective. So there are 5,000 regional airports. What's your perspective on the acceptability or reception of the airports welcoming your service, and from both the financial revenue perspective and the community perspective? Thank you.
So I think it's an excellent question, and it's going to very side of it. The way we have a technology right now, there's no way to know if there's a pilot or no pilot on board, right? So it's no different from current aircraft. And those airports already have handled the issue of noise, right? In some places, like there are complaints, but an airport receives air service and airplanes, and so the noise, it's already accounted for the fact that it's an airport. The communities, when they see the benefits, it's going to, I'm sure they will like welcome it. If you think about why we have all those airports, it's to connect communities and to have an economic impact. So as we bring the airplane and we bring packages, we need to hire somebody to unload the packages, right? We're not just going to dump them and nothing will happen. When you bring passengers, it means you're going to need to have transportation close to these airports. Small businesses are going to be able to operate at some of these locations. For instance, one of the routes we have, actually a couple of the routes we have, so most of the routes, if you look at them, we have a hub where you have the airliner that comes, drops the packages, and goes out. And the airplane comes back at night with it goes out full, it comes back with almost nothing. We have a few places where it's actually the opposite. We have up in the northwest, in Tillamook, there's a cheese factory, and the airplane comes back full of cheese, right? Without that airplane, that small business would not be able to sell as much and be as profitable. We have another location where I think I forgot what they ship, but same thing. The airplane actually comes into the large airliner full and goes out empty. So it really shows that many businesses are able to flourish and to be successful thanks to the small airport and that service.
So some of these airports already have issues with like runtime waits or like runway waits, or like the plane can't have, there's no open gate or something for the plane. So I was just curious generally what you think the impacts on like infrastructure of having a lot more planes like this will be. And then also you mentioned briefly about how if you're transporting people with planes, well, someone might take a regional trip with their car because then they want to be able to drive their car like locally at their destination. So that would seem to also have an infrastructure impact on like the local transportation required. So kind of like these infrastructure impacts, yeah.
Yeah, absolutely. So the first part of the question was around the gate and the availability of this airport. So as I said, right, 70% of the traffic goes through 0.6% of the airport. So those are the airports that are congested right now. All the other airports, there's plenty of room at this stage. When we get to saturate those airports, I'm going to be very, very happy. It means we are successful, and we need to build more parking space at those airports. And the second part was, yes, transportation like around the small airports. So that's part of the economic changes that we're going to bring, right? If you bring people to the airport, then you can start having like car rental services, right? You can start having Uber. So it's going to provide job opportunities for the people in those communities because they will have more travelers, right? If you have more travel, then you can open a coffee shop. You can open like a bakery right close to the airport because you start serving the passengers. So that's how just the transportation has a huge economic impact around these communities. So again, you know, if you fly your small Cessna to one of those airports, many of them have what's called an FBO. So it's a small place that will welcome you, will fuel your airplane, will wash it if you want it to go washed, and then they have rental cars. So this is a problem that is already solved. It will have to be more developed than it is, but it's a solved and solvable problem. It's a good problem to have.
Actually, I'm very motivated by this 1.2 million miles. It's really fantastic that you've flown 1.2 million miles. How many million miles will it take to reach this 10 to the power minus 9? And you know, is there a path to certification of an autonomous system through the current regulatory regime? You know, where you can cut that high bandwidth video.
Yep.
You can take out the safety pilot, or does that really need a change to the regulatory regime? Is there two parts to my question?
Yeah, two parts to the question. So first is how many miles will it take, right, to certify it? The answer is the number of miles doesn't matter, right? We hear all the certifying cars like bragging about how many miles they drive. This is because they need to collect data and to ensure that they're good. To certify an airliner or an airplane, you don't even have to fly a lot, right? All you need to do is you come up with a test plan and show, I'm going to show you that I can do all those things in all those conditions, and then you demonstrate it. And once it's demonstrated, it's enough, right? So for instance, to certify an auto-land system, right now, like a lot of the larger liners are able to land by themselves, right? And it's certified to 10 to the minus 6, so one failure per 1 million flight hours for the auto-land. But they don't do 1 million landings. What they do is they do a lot of simulations, and then they validate the simulation by doing 100 landings, and they show like, look, my simulation matches reality, therefore I can trust my simulation, and I have done a lot of simulation with like all the corner cases or the weather conditions, so I can trust this, and then I validate with a subset of those. So here's going to be the same approach. It's a mix of simulation, model development, as well as...
So simulation technology is a very critical part of the company's
absolutely, yes,
technological capacity.
Yep. And then the second part of your question was, are the regulations here?
Yeah.
So there are two parts of certifying this system. You have certifying the aircraft, right? And in what we're doing, it's an existing aircraft that already has a type certificate. It has an engine that is certified. What we are adding avionics to this airplane. We are adding sensors, and all we have to show is that whatever we add is not going to cause the airplane to fall out of the sky, right? The second portion is, am I allowed to fly this airplane into the airspace, right? That's the operation side, and that's the airline portion of it.
VFR and IFR, right?
Yep. So again, starting at the top of the FAA, you have a part that certifies the ability to have an aircraft and you have the other branch that allows you to operate this aircraft, right? And the portion about being able to see and detect other airplanes, this is on the operation side.
Yes.
So the regulations are in place. Right now, the regulation said the pilot shall see other airplanes and maintain a safe distance from them, right? What we have to do is show that, well, the pilot is actually the airplane, but we can still meet the intent of the regulations with our system. We still have a way to show that we can see other airplanes and we can safely avoid them. So we're not asking to change the regulation. What we're doing is showing that we have what's called an alternate means of compliance, an equivalent level of safety. So we can do the same function in a different way.
But has the FAA said anything about this? That when they allow this reinterpretation of a rule?
Yes, it's been done many times for different technologies. For instance, Cirrus. So Cirrus, they built like a 4-seater airplane, and they're the first airplane that has a parachute on it, right? So if anything happens to you, you can pull the parachute opens, and you can land. When you certify a small airplane, you have to demonstrate that if you enter a spin, like in Top Gun, right? You all see Top Gun? Yeah. The first one, why did Goose die? Because they entered a flat spin and he ejected and hit his head. So you have to show that if you enter a spin, you can recover, right, in a small airplane. And typically you do that by you enter a spin and you have a pilot that like does the right maneuver and saves the airplane. Very dangerous maneuver. What Cirrus did is say, well, I don't want to do this. I'm going to show you that with my parachute, I can still save the airplane. So even though the regulation said initially you have to demonstrate that you can get out of the spin by using the rudder, they said no, we're going to show an alternate means of compliance to this regulation. The regulations, the intent is to say that I'm spin resistant. I have another way of doing it. So here's the same, right? We just want to show that we have the way to do the same thing, just in a different manner.
I see. So you literally meant what you said that earlier, that it's very difficult to change the regulatory regime or the air traffic management regime.
Yep.
So you're going to try to get yourself certified in the existing regime.
Absolutely, yeah. We don't want to change anything. We just want to say like, we're doing the same intent, just in a different way.
Yeah, so are you allowed to, are you certified to fly overpopulated areas?
So currently we have an experimental aircraft, so we cannot fly overpopulated area. Once we are certified, yes, we can fly wherever we want. But again, we want to be very progressive, so we're going to start deploying the technology probably over like intra-island. So you take off, you fly over the water, and you go to land in another island, which is a perfect example of this technology, right? You save, like when you have to take a boat, it takes hours. Here, like it takes minutes to go from one island to the next, and you don't put the population at risk. It's a great place to get started.
And how much are you going to charge? Like, for example, okay, I want to take, I'm not going to take my car. I prefer to, you're mentioning that you're not going to go into the sort of really high end, so, and it's going to be cost efficient.
So eventually when we get to this regional passenger transport, when you have electric vehicles, we believe you can get to a price point which is similar to the one of a car, right, in terms of price per passenger mile. So like around 60 cents, because the vehicle is going to be more expensive than a car, of course, but it's going to be more efficient, and then it's a shared asset. So those vehicles, like fixed wings, electric vehicles, can become really cheap. What is expensive currently on an aircraft is the maintenance. So the engine is very expensive, like those turboprop engines are extremely expensive. And if we go to electric motors, this is way, way cheaper. So right now, by removing the pilot and moving on the ground, we estimate we can save 15 to 20% of the cost of the flight. But once you get to electric and autonomous, you can dramatically reduce those costs. So I don't have a price for now, but it will be way cheaper than what it currently is.
And you're sort of buying the Cessnas that you're going to put
Yeah, so right now we are, it's a mix of airplane that we buy and lease. And when we deploy the technology, it's on the one that we own for now. Yes. So if you think about, so two main customers, FedEx and UPS, they operate differently. So FedEx owns their entire fleet of airplanes, and then they provide the fleet to an operator, and they pay for the fuel. So the operator, all they have to do is like take the airplane and fly it around and find the pilots, which is actually is a big deal. For UPS, you have to come, they give you a contract and they tell you like, I'm gonna drop packages here at 7 a.m. I want them over there at 9 a.m. Good luck, right? And here's some money and you need to be 100% service guaranteed, 98.5% of the time on time. So really stringent requirements, but you bring your own airplane. So right now we're operating for UPS, so we bring our own airplanes.
You mentioned 10 to the minus 6, 10 to the minus 9. What is, when you're flying passengers in an unpiloted aircraft, what is your safety target?
That's an excellent question that right now, like the FAA hasn't said anything to it about it. So there's what's called like the safety continuum in terms at the FAA, based on the aircraft you have, how many people you have, different levels of safety. Starting at 10 to minus 5, roughly 10 to minus 6 for like the small, like one-seater, two-seaters, all the way to 10 to minus 9. But actually, if you look at the larger liners, they're 10 to minus 12, even like 10 to minus 13 at this stage, like level of safety, so it's huge. Where we fit around here is like 10 to minus 7, 10 to minus 8. So that's where we're targeting. The EASA, so in Europe, they said that the eVTOLs, so like the Joby-like type of electrical vehicle and takeoff, should have 10 to minus 9. And the reason is that people said like you're going to have thousands of those flying over the cities. So if you have thousands of those flying over the cities, 10 to minus 9, like that's still like some of them falling out of the sky regularly, right? Which we want to avoid. So when you think about it, it's a combination of how many you have in your fleet times number of flight hours, time exposure time to get to that.
I guess my question is somewhat, you don't have a person on board, so if you crash, you lose a machine, but...
Yes. So for us, we lose money. It's a really bad exposure. PR. And also that's, we just need to be able, like if we detect, as we're describing, safely reroute to not expose the public.
Last question. Thank you. You mentioned earlier to use electricity to turn down on the cost of flight. Is turning electric in the long run of the vision of Xwing?
Yes, I mean the autonomy is the unlocker, right? Once you have autonomy, you can open the market, but we don't want to build more like, dinosaur juice sucking engines, right? We want to be clean. So first the autonomy, and then like electrification will come later.
Great. Thank you. Please join me in thanking our
Thank you.
Thank you for a very provocative presentation.
Provocative?
Token of our appreciation.
Oh, thank you. Thank you very much.
Water bottle. Thank you
awesome.
for being
thank
here.
You.
It was terrific. Please, if you want to speak to Maxime a little more about his technology, his company, feel free to come up and chat with him.
We're hiring now in the future.
Magic word.
Go to xwing.com and we have some, we need like all kind of skill sets. So that's really important. Like when you think about aerospace, all kinds of skill sets.
And the website is?
Our website, xwing.com.